And we are live. And everyone, welcome to Climate Chat. I'm your host, Dan Miller. And today we have a very special returning guest, climate scientist Leon Simons. Leon's based in the Netherlands, and in his climate work, he's perhaps best known for being a co-author with Jim Hansen on a groundbreaking paper, Global Warming in the Pipeline, from last year, soon to be 2 years ago, I guess, in 2023. And
Yeah,
he's
November
also
20.
one of the world's experts on the impact of shipping emissions and aerosols in general on warming. And that's been a big thing the last 2 years. In fact, the rest of the climate science community hasn't fully woken up to this. But Leon's going to take us through some of the latest data, including what's been happening and what may be happening in the future. And so rather than do Q&A from the beginning, we're going to turn it over to Leon and let him update us. So Leon, welcome, and it's all yours.
Hi, Dan. Thanks. Let me get my slides ready. Yeah, so a lot happened in the past year, as we all know. It was quite a crazy year. People thought 2023 was crazy, but 2024 was quite a bit warmer. So let me get my slides. It's working, share. Yeah, opening slide. So what we need to talk about, I think I want to go through these points, spend like 20 minutes I'll try to keep it relatively short to cover these points. So why do we care about a few tenths of a degree? I think it's good to cover that. And then how much hotter was 2024? And I think it's all about the base, right? The baseline. And is there acceleration? So, and then talking about greenhouse gas, aerosols and clouds and the regional extremes, the AMOC, and then what's next in discussions, etc. So first, just to, of course, we all know about the Paris Agreement, but what was the Paris Agreement really about? It was about mitigating risk and keeping warming below 1.5 or 2 degrees, and trying to keep it below 1.5. And it was mainly about risks, right? And then they use a baseline to make it somewhat measurable. They said just keep warming below 1.5 of pre-industrial period, which is here they use 1850 to 1900. And it's a bit arbitrary and hard to measure, and maybe that was a bit of a goal because that helped, of course, for all these countries to come to agreement, because it wasn't like very hard goal that needs to be reached, right? It's still a bit vague. When do you cross it? What is the baseline, etc. So and which data set do you use? So there's a lot of wiggle room there in a way. But in the end, it's not really about the math and about the exact number. It's more about mitigating risks. And I think what's important before we go forward to note is that this 1850 to 1900, depending on which baseline you use, but also I think for all the baselines, what the IPCC says is that about 0.1 degrees Celsius above 1750, which is really what we often use as the real baseline for when the Industrial Revolution started. And of course, emissions increase gradually, but that's when, especially for the forcing, so what causes the climate to change, we use 1750 as the baseline, as a pre-industrial baseline. And then going to talk about risks, I live in Eemnes, which is a town in the center of the Netherlands, which used to be at the Zuiderzee, the Southern Sea, which has been turned into land. But the Eemnes is, in a way, the name is quite famous in the Paleo climate community. So the climate community that looks at the climate of the past. And why is that? That's because someone 150 years ago was doing some research on soil and drill holes from where they, for example, where they were drilling for water wells for beer. He would take those cores 150 years ago and look at what came out of the ground, let's say 10 meters deep. And what he found were these very small shells, and these were seashells at the location where they used to be, where there was now land. And then he looked at those shells with a microscope, and he discovered that those shells, he had seen them before in the Mediterranean, which is about 2 degrees Celsius warmer than temperature we have here now. And that was the discovery of a warm period before the last ice age, called which he called the Amian. And that's a very important period, because at that time global sea levels were 5 to 10 meters higher than they are today, and they can help us a bit to try and understand what the future climate will look like as we are causing global warming. This is from a paper by James Hansen, and here he used the anomalies are relatively to 1880 and 1920, and then comparing them to different studies which assessed the climate of the Amian, which had a temperature anomaly of before that 1880 to 1920 baseline of about 0.5 degree to 1.5 to 2 degrees warmer than what they use here as a pre-industrial base. And we are now in 2024 using the NASA GIS data set, the same as James Hansen used, at 1.55 degrees Celsius above that, which is already above some of the estimates. And especially if you look at sea surface temperatures already higher than they were during the Amian, or reaching there now if you look at global average temperature, looking at the higher estimates. And that's really important if you live, for example, like me, below sea level, right? Because if it's this warm, and it takes time for all the ice to melt, but if the ice starts melting, the sea level will start rising, and we could have again 5 or 10 meters of sea level rise, even with the current climate, right? Without additional warming above what we have today. And then looking at, again, just because I said it's about the base, right? It's about the baseline. So James Hansen used 1880 to 1920. Kevin Schmidt often uses the 1880 to 1899. Kevin Schmidt is a successor of James Hansen at NASA GIS. And I think that's these baselines. I think this shows that if you just change the base period, the average period of the global climate to another period, it does change here. For example, in this, it seems small, but 0.05 of a degree is still it's a change. And then going to, I think, the next step to see, okay, what was the climate? How warm was it in 2024? I just want to go back to July 2023, when the Earth, when the El Nino predictions started to come in, and we started to look at how warm will 2024 be. And I think I really, this is not to call anyone out. It's just, I think it's really important for climate scientists to estimate what the future will be, like also for the near term. And I think very few do that. I really appreciate those doing that, like Ziek Hausvater and like Kevin Schmidt. Here's Ziek Hausvater, and we didn't know, of course, how warm it will be, how strong the El Nino will be, for example. And he estimated 2024, 1.5 years ago, to be about 1.4 degrees using the Berkeley Earth data set above pre-industrial. And and now it is about one. We don't know exactly how high Berkeley Earth will be, but I think a bit above 1.6. So that's about 0.2 degrees Celsius warmer than this estimate. And of course, Elliot Jacobson, he often does these bets, right? These fake bets to see, okay, what do we think what will happen? And he said he would give a 10 to 1 odds for 1.7. And I said, because I said with a super El Nino, we might have 1.7 degrees Celsius above pre-industrial with Berkeley Earth. So I said, okay, if I was a betting man, I would put 1,000 euros on it if the El Nino reaches 2 degrees Celsius. And I'll get to that, whether El Nino was this strong. And why do I say above 2 degrees Celsius? Because that's what they say is a super El Nino. A very strong El Nino, which has a significant impact on the global surface at temperatures, which cause these really very strong global records to be broken, right? And this is from Gavin Schmidt also. Here he shows in blue the 2023 estimate, and here I think it ended up about here. So there was really a big deviation from the estimate, right? And that's I think what he said is 0.2 degrees Celsius of warming that he couldn't explain when they had a study on that. And he also had a prediction of 2024, which was about the same, right? It's a very small. And I think that here again, this is from thanks to Ziek Hausvaller, he compiled those estimates of 2024 at the start of this year. But it ended up about 0.12 degrees higher than 2023. And of course, the data still needs to come in from the different data sets, but let's see what it shows. But I think the most will show about a bit above 1/10 of a degree Celsius warmer than last year. And here it is from ECMWF. I showed the months since 1970, and you see that the last year, this year is about 1.6 degrees Celsius warmer than that's 1850 to 1900 baseline again. So if you look at the 1750, it might be even higher, warmer. It might be 1.7, and that's for the Paris Agreement. You could say what's right. I think maybe 1850 to 1900 is okay to use there. But if you want to understand the greenhouse gas forcings and the aerosol forcing, it's better to use 1750 to really understand what causes this change and how much change. And yeah, I'll get back to that later. So then you see, 1.5, 1.6, those are 2023, 2024. And then if you look at 2015 and 2016, where what is 1.1 and 1.3, and after that it didn't cool down very much after that. There were no temperatures below 1.1 after that. So we might already be at 1.5 degrees Celsius of warming above the pre-industrial baseline looking at this data set. I think that's important to know. When will the community or the government or the media, or when will they or we agree that we have reached that point? I think not today, but with a few more years, and if we have a La Nina, for example, which is not very much below 1.5 degrees Celsius, I think that most will agree that we've crossed that threshold. And what that means, that you can discuss that again. So did we reach a super El Nino last year? Did it reach above 2 degrees Celsius warming? I think these are since 1959, and you see there was a very strong El Nino that was really a super El Nino in 1998. And then again, just look at all the lines together. And then because here the blue and the orange are similar, right? And then here you see 2015, 2016, it peaked about the orange peaked about the same as the other orange, but the blue peaked higher. So what is the difference? I think the difference is that if you look, the El Nino is determined on the tropical Pacific, the temperature of the tropical Pacific in a certain mid latitude, sorry, in the tropical region, the certain latitudes, how much they change from a certain average. But if you look at that's a 30-year average, but this is 2016, and we don't have the data, 15 years of data after 2016 yet, because it's not 2030 yet, right? So that's why we don't really, El Nino is less good of a indicator for the short-term climate. And that's why there's also a relative ocean Nino index, which I showed in orange, which I plotted in orange, which shows that relative to the rest of the tropics, how warm this region is. And that gives, in a way, a better indicator of how strong also the past El Nino was, right? This El Nino. So and here you see this is a 3 month average. If you just look at El Nino, it peaked at 1.95. But if you look at the relative, it peaked at 1.5. So it wasn't very strong. It wasn't super strong. So we didn't have a super El Nino, but we still had we still broke all these records by a very large margin, which many were surprised about. And then and also when we talk about acceleration, which I'll get to, because the next question is, okay, is this normal? Is this expected? Or is this just linear warming? Because between 1917 and 2010, there was a warming rate of about 0.18 degrees Celsius per decade. Is this linear or not? I think what's important, if you look at the last decade and compare it to the preceding decade, then it's important to know whether, for example, El Nino played a role there. And if you look at this relative aspect, if you just compare these two blue lines, the average of the past 10 years, there's a bigger jump than if you just compare these orange lines. So then if you look at this, El Nino was about the same strength. So then going to, I think this is a bit complex for now, but just showing this is 2015 to 2016 El Nino in purple, global surface temperature anomaly above 850 to 1900 in purple, and the dotted line shows the El Nino, which as you see is stronger than or higher than the red one, because the El Nino from the past El Nino was less strong than the 2015 to 2016 El Nino. But temperatures in red, the temperatures of 2023 and 2024, December still preliminary, were much warmer. If they were 0.35 degrees Celsius warmer than for the same period of the past, the super El Nino of 2015 and 2016. And then if you, that's 8 years, so if you take that for a decade, if that would have been a decade, you would have 0.43 degrees Celsius of warming within a decade. So that's really a lot of warming, of course. So there will be a doubling. And then again, here I show from NASA data and the ECMWF data set. You can look at, so here I compare these decades of, to do 2 decades, so 2004 to 2014, to 2005 to 2014, comparing that to 2015 to 2024 for both dates. So you see that there was the increase per decade about 0.33 degrees Celsius. And then again, here it's about 30. And you can see all these different ways. Of course, a bad way to do this is to look at what was the temperature a decade ago, which is for 2014, sorry, and 2024, that's a bad way, because then you cannot compare one year with the next because of indeed these natural variabilities like El Nino, right? So then you would have a warming of even more than half, or more, even more than 0.6 degrees Celsius in a decade. Or if you look so there's different ways to look at it, but I think this really shows, whatever way you look at it, this all shows that this is the strongest warming rate in history, in all data, in every data set I've looked at. But I think that's really important to take into account. That really shows that warming has accelerated, also for the surface, not just if you look at global ocean heat content increase, for example. Yeah, maybe you have questions up to here, Dan, because it's taking a bit longer.
No, it's good. No, just keep going. I think it's good.
Okay.
I have lots of questions, but I'll hold them to the end.
Yeah. So what causes this warming? I think I showed this to a friend, and he says, yeah, every time I see this, I cannot believe this is real, right? This is the total greenhouse gas forcing from 130,000 years ago to today. Which of course this was the Eemian, as I mentioned, the Eemian. This was the warm period when sea levels were 5 to 10 meters higher than today, and this was the Holocene, and now we are here. That's just looking at all the greenhouse gases as was also part of global warming in the pipeline paper. We showed this data. We're looking at different methods to estimate this, but looking at all these greenhouse gases together, so methane, CO2, etc., and then use that to estimate the value of in watts per square meter of forcing, which maybe I think I've explained that before, what a forcing is, but that's the amount of heat that's forced into the system by these greenhouse gases into the Earth system for every square meter of Earth surface. And the Earth has a surface of 510 million square kilometers, which is 510 trillion square meters. That's a lot of square meters. But there's some questions about why the Holocene, which is this period, the greenhouse gases increased, but there was no warming, or there was even cooling. And also, if this was almost as high as this, haven't sea levels risen much more? So these are questions which don't have a lot, where there are still quite some answers. Sorry, there are questions where there are still some missing answers for. And in Global Warming in the Pipeline paper led by James Hansen, one important hypothesis that was put there was that part of this was mitigated, this increase, because the greenhouse gases started increasing, also because of the agricultural revolution. People started burning forests, people started growing rice, which emit methane, land clearing. So a lot of changes and a lot of emissions of greenhouse gas over thousands of years. And what we put forward in this paper was that this could be mitigated in part by an increase also in air pollution. And it might be hard for people to imagine that the pre-industrial civilizations were able to already control, in a way, the global climate by increasing greenhouse gases, but mitigating the warming by increasing also aerosol emissions, which reflect sunlight and make clouds brighter. But I live and work often also in developing countries. I work in Ethiopia, for example. I've been to Madagascar, and I've been around the world. And what you see there is people burning a lot of wood for cooking, but also burning a lot of grasslands. Because and that is often in times when during the rainy season, when the grass is wet, and you have it's incomplete combustion because the fires don't burn very hot, which produces a lot of smoke. If you if you make a fire and your wood hasn't dried well, there'll be more smoke than if the wood has dried well, because it takes also a lot of energy to evaporate the water, and then the fuels can combust very efficiently, and you have this incomplete combustion which produces all these aerosols, which also reflect sunlight or absorb this sunlight in the atmosphere rather than let it reach the surface. So what we propose there is that this also contributed to cooling, well, and compensated for the warming effect of these greenhouse gases, where we said starting about 6,000 years ago to 1750, there was a increasing aerosol forcing from of half a watt of cooling between 6,000 years ago and today, or to 1750, sorry. And if you add that aerosol forcing, you see that this forcing is very stable. So that can help to explain why the temperature of the Holocene, so the past 6,000 years, 10,000 years, was so stable, because we helped to stabilize the climate by emitting greenhouse gases and emitting aerosols, and that stabilized the climate. And then also, if you look at the EMIAN is then much higher because you shift the baseline. Yeah, that's also about the baseline, because you shift the baseline up by half a watt, because 1750 was cooled by half a watt. Then it shows that the EMIAN was much, the climate forcing of the EMIAN was much higher than if you don't take that into account. And then if you look at these two together, you see, okay, of course I also added the greenhouse gas aerosol forcing here on top of 1 watt per square meter. So that's still because we increase aerosols after 1750, causing more cooling. So that and also that makes the last glacial period less negative than if you wouldn't take that into account compared to 1750. You see, because this is more negative. This is about 3 watts, and this is about 2.5 watts. It's a bit counterintuitive maybe, but this is what the data shows. And then but this during the last glacial maximum, global sea levels were over 100 meters lower than they are today, because there was so much more ice, because it was much colder globally. There was much more ice on North America and Europe, and that caused the world to cool down.
Mm-hmm.
And that produced ice and the 2 degree sea levels. I think that I'll just skip this, but if people want to,
that's over for Americans, that's over 300 feet. So back in the last ice age, sea levels were over 300 feet lower than they are today. Florida was, I think, 3 times wider than it is today. You could walk from Russia to what's now Alaska. I mean, that's
and you could walk through. England was part of the continent.
That's right. England, you could walk to Europe. That's right. Yeah. And it wasn't that long ago. I mean, like 18,000 years ago, right? So.
Yeah. So then indeed, it started melting quite gradually. Also, because if you look at this line, it might seem quite steep, but this is 10,000s of years. So this might seem steep, but it's really not as steep as this line is.
That line is. And that's why people don't really understand that when we talk about sea level rise of 10 feet this century, which sounds a crazy large amount, it's really just a tiny fraction of the drop in sea level in the last ice age. So we're really playing with fire, I guess, is an apt analogy. But keep going.
Yeah, so these are modeling studies showing that if you look at they use the greenhouse gas concentrations, and if you look at the models, there should be warming in over the past, it is 12,000 years. So there should be warming also in over the past 6,000 years. If you look at, if you put all these the greenhouse gas concentrations, which are taken from ice cores, from these small bubbles in ice core, you can, if you put that data into a climate model, you would estimate that there would be global warming over the past 6,000 years. But if you look at the if you look at the reconstruction of the data, it is 12 to 6,000 years ago there was warming, but from 6,000 years ago to 1750, there was cooling, especially in the northern hemisphere, and that's in part because of the solar cycles, the Milankovitch cycles, but also even the climate models show that there should be warming. So then why is that? And we estimate that in part is because of these aerosols.
Right. And so that's when agriculture was going on and people were burning. People don't realize, but I think it's a third of all non-ice covered land on the earth is used for meat production, cattle grazing, growing food for cattle and things. And that started long, long ago, and people burning down forests to clear land. And each
Yeah,
little one doesn't have a big impact. You add it all up, it has a huge impact.
yeah, and it's also because of like now we burn biomass very efficiently relative to how we did it before. And most, I think most people who listen to this and most scientists also studying this, I think, don't spend a lot of time sitting in huts in Africa burning biomass or raising cattle on the highlands of Mongolia or something, right? So that there's really if you spend time with those people and you see what they do to survive, they just like light the mountains on fire and wait for the fire to disappear and the rain to start, and then they have these fresh grass which animals can eat and grow fat on, and then it makes sense if you understand, but it's often not in. I think it's not surprising that this is has been overlooked, has likely been overlooked, and because and I think it's the same with shipping. So why we'll get to that, but has the effect of shipping emissions been largely overlooked? The sulfur emission from shipping, I think because most scientists don't spend a lot of time on the oceans, right? And or let alone study the regulations these super tankers have to adhere to. There's
But
some
not just
exceptions, but yeah.
But not just in the developed world. I spent a lot of time on farms in Mexico because of one of the companies I was working with, and they're taking crops, certain kinds of crops, and just burning them, to clear them up and to help the land for later use and things like that, and filling the skies with smoke. And it's just it's happening today. This is not like not too far. I guess there's air pollution regulations in the United States that might prevent that kind of thing, but most of the
Yeah.
rest of the world, India, it's a very popular thing to do as well. So,
Yes, exactly. So these 2.5 billion people still using biomass for cooking in
mhm.
relatively inefficient cooking technology with relatively inefficient cooking technologies, as well. And then someone asked this question to me today, like what impact does it have, and how does it compare to sulfur emissions, and that's really complex, right? Because sulfur in a way is very nice and simple to study because it's just these very small. It's emitted as SO2, sulfur dioxide. It's a gas, and then it forms these bright white yellowish particles which reflect sunlight and act as condensation nuclei to create clouds and
Mhm.
make clouds more white. That's very uncertain what the effect of that is on the climate. There's so many uncertainties on where it is emitted, how high it is emitted, what time of the year it is emitted, and what is the background load of aerosols from plants, from algae, etc. It's already very complex, but what is in the smoke from biomass burning, cow dung, different species of trees, different humidities, of the different wood moisture content, all these aspects is so much more complex even than that. And then like how many tons per day. So and whether it rains or not. So there's so many variables there to include.
Mm-hmm.
And what happens if it deposits on snow, and then it absorbs sunlight, causing the snow to melt, right? All these that's really even more complex. But yeah, that's of course but the health effects of these air pollution, especially in households where they are cooking with the biomass, that's really bad. About 4 million people, mainly women and children, die every year from using biomass.
Mm.
So that's I think I think that we should start there, and that's what I'm working on. But I think that's really where we should start to reduce air pollution first, and of course, so reduce greenhouse gas emissions, etc. But if you want to reduce health impacts of aerosols, start in the kitchens of mothers and with their kids. Yeah. So let me see. Yeah, I think do you have questions about or comments about because I can go on and on, but
Well, okay. Well, by the way, I've always looked at just the warming chart since pre-industrial of global warming, just the temperature chart. And at the beginning, it doesn't go up. It kind of goes down a little bit, then it comes up, and then it goes up at World War II. Well, and then it drops after World War II, and you go like, what's happening? Why isn't it just going up as we release more greenhouse gases from the start of the Industrial Revolution? In fact, it went
yeah,
down at the start of and it seems to be well explained by aerosols because global warming is caused by the cumulative emissions of CO2. And at the
yeah,
beginning of the Industrial Revolution, cumulative emissions were small because it was the beginning. And then we got the we got the aerosol, the smoke from the coal plants, and that was
yeah,
cooling the earth, and that kept happening. And then after it went, the temperature went up in World War II because many industries were shutting down because of World War II. And then after World War II, we had reindustrialization, which
yeah. So
cooled the
this
planet.
shows 1950 to 1980, where you see the best
Let's see,
estimate
where are we?
aerosol forcing
Oh yeah, yeah.
from
But that's before. Yeah, you got to go back to the Industrial Revolution to really see this whole
yeah.
effect.
I would have to look it up, but I think
I thought
you know
that's a great data set for calculating because we probably have a pretty good estimate of what our aerosol emissions were back then. And then when we passed the Clean Air Act in 1970, that's when global warming started its steady sort of semi-linear rise
yeah.
until recently, which is the part you're talking about, like
Yeah,
what happened
and that's
recently.
when I think that's what you see here. The aerosol forcing stabilized more or less
Hmm.
because of indeed the Clean Air Act from Bush to
Hmm.
the Bush senior in the United States and in the European Union, where a lot of clean air regulations came into effect in around the 1980s, where you can see that those decreased the sulfur emissions, especially sulfur emissions, and then over China and India and around the world, that air pollution increased until about 2010, when the air pollution started rapidly decreasing globally from shipping,
Hmm.
from China, from other regions. So global average, and that was this line. So this is the greenhouse gas forcing in red here.
Hmm.
The and then this is what you mentioned, that there was cooling or even less warming,
Yeah.
especially over the northern hemisphere, because the air pollution aerosols increased. And of course, this is uncertainty. There's a big. I don't show the uncertainty margin here, but especially over the northern hemisphere, there was even cooling indeed since around
Hmm.
between 1950 and 1980, and then aerosol emissions stabilized, and then but the greenhouse gas emissions kept increasing. and then the net forcing started to increase as well, reaching the global greenhouse gas forcing reaching about 4 watts per square meter, including tropospheric, ozone, and stratospheric water vapor, which are forcing agents as well, and methane and nitrous oxide and all the greenhouse gases combined. Looking at the IPCC method, we are at about 4 watts per square meter, just looking at the greenhouse gases, which is equal to a doubling of CO2. Increasing CO2 from 280 to 560 parts per million. You can debate whether it was 278 or 280, but yeah, so it's roughly right? And then the greenhouse gas forcing is indeed, again, quite uncertain. I think what the IPCC method gets very wrong is what happened to the aerosol forcing, because they have it the most negative, so the most cooling from aerosols in the past 8 years, in 2023.
Is that because of China? What do they think?
And because they they assume that all aerosols are equal.
Okay.
But in reality, some aerosols are more equal
than others. Yes. Okay. And shipping aerosols in particular, where they're over a dark blue ocean that's absorbing 80% of the sunlight, and you form a cloud that reflects 80% of the sunlight, and there's no other factors. Like in China, where you have pollution, it might be over light-colored land, so even if the pollution goes away, the impact's not quite as much.
And what they also assume, Forster et al., is that all these boreal forest fires were also anthropogenic aerosols. So, but not the CO2 emissions; those were not anthropogenic. And then that these aerosols are also equal to sulfur, and that in a way that this all just averages out globally and causes a decrease in the net forcing, anthropogenic forcing. But
I see. So increased forest fire then was a big part of that then.
Yeah, but
there's this number here.
But the forest fires from Canada, much of that deposits on the Greenland ice sheet and on Arctic ice, and it's higher latitude. So, and that could all even cause more warming rather than cooling, especially. And another study shows that decrease in aerosols from shipping and from land could even increase forest fires in boreal regions because of more dry.
So your aerosol affect your yellow line, well, the bottom orange, I'm not sure what color that is.
This observational data.
No, but I'm saying that does not include albedo changes due to Arctic getting darker from pollution or clearing trees and having different colored land underneath.
No.
It's only from aerosols in the air, okay, in the atmosphere.
I changed the y-axis here just to zoom in on this. You see that this is the 2023 estimate going up to 2022. And this is 2024 estimate going up to 2023. And there they show that 2023 at the lowest aerosol forcing, so the most negative aerosol forcing in 8 years.
But this is not data. This is a calculation.
This is not data.
Right, this is a calculation.
But this is the IPCC methodology. So it's not data, but it's IPCC methodology.
But they're assuming all aerosols are equal when that's not it.
But they published this. They published a study on climate indicators, but they don't include crucial climate indicator, which is how much sunlight is absorbed using these NASA satellites, which I show here. So because this enormous increase, that can only be explained. I think we'll get to that by feedbacks. So climate feedbacks, less sea ice, less clouds from warming, or aerosols or aerosols. And I think it's a mix, of course. The sea ice is decreasing, snow cover is decreasing, cloud cover is decreasing, aerosols are decreasing, and then the question is how much does each contribute? But you need to include that data. If you publish a paper, because that's what they did, they published a paper being an annual update of the IPCC methodology. But the IPCC AR6 Worker 1 report included this data. but the new studies don't include this data, which shows that how they can reach, which shows that maybe that doesn't help them to see that this is very wrong, because this is very wrong. You cannot decrease the anthropogenic aerosol forcing while you mitigate sulfur emissions over the oceans by 80%. That is not right.
Well, if everything's equal, even though they're not, then maybe you can come
Yeah,
up with that. But
you can, but
well,
that
speaking of
shows.
that,
Sorry?
I'm going to ask you a sort of a basic question. So, your paper with Jim Hansen, you made the claim that reducing sulfur emissions from shipping by 80%, starting in 2020. I guess it started in 2015, but the 80% rule kicked in 2020. And then we had a La Nina during that time. So things were not as hot as they would be, but when that La Nina went away, all of a sudden this effect of getting rid of that sulfur was very dramatic. So you made this claim, and a lot of scientists said, no, 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 that's not true. Shipping sulfur is only X% of all aerosol emissions. It's a very small amount. Yeah, and literally, I believe the numbers they estimated for the warming that would be caused by that was 1/10, roughly 1/10 of what you and Jim Hansen were saying it is. And that was almost a couple of years ago or a year or two ago. We had a lot of guests on Climate Chat talking about this, and some still are saying that. But now it's been 2 years, right? Now we have 2 years of data, and no one else has an explanation except for you and Jim and the others who agree with it of what's
Yeah, so
happening.
we have now 5 years of data
Well, I meant of
of
the
the
exceptional warming where the climate
yeah.
scientists themselves are saying we don't even know what's going on here.
But that's I think that's just looking at global surface air temperatures. I think that's not really the right way to look at things. I think, right? If you can, it's that's such simplification.
Yeah,
That's,
sure.
I think, and I wrote that in at the start of 2023. I wrote an article, I wrote it on X, on Twitter at that time, saying, okay, this will be the year when people who don't look at radiative fluxes and energy imbalances and zettajoules will start to realize that the accelerated warming from reducing our air pollution. And I think that's what we are now starting to experience. Every media article writing about the extreme warming in 2023 and in 2024 almost at least writes about desulfurization of shipping, right? I think they still get it wrong often. They still underestimate the effects.
Mm-hmm.
And I can dive into that as well. And James Hansen will publish a paper on that, I think, very soon. I don't know exactly when.
And we're going to have Jim on to talk about that paper, by the way. So it's a nice, everyone should know that. And it'll be pretty soon, I think, in the next month or so, we'll have Jim on to talk about that paper.
Yeah, great. Look forward to that. I already read it. So I think that will, I won't go into the details there, but I think I think that will help explain what's going on. And
But
it
I was
builds
going to
up.
ask you whether other scientists are coming on board, given there's no other explanation for 2023, 2020. Okay, maybe 2020. Oh, it's a La Nina or whatever. El Nino, as you were explaining, not really, but they could claim. They can't claim that in 2024. So they have no other explanation. My question is, are more scientists getting on board with your explanation for what's helping cause that warming?
Um, I think I think there's quite a lot of skepticism, and I think that's very natural in science, and I think that's a good scientists should be very skeptical, especially about their own work, but also about the work of others. And I think it also, can you imagine if you've been studying the climate and if you're studying the oceans and then you learn in 2021 that in 2020 the sulfur emissions over the oceans were reduced by 80%. And it's hard to imagine that you've missed that, right? I think that's where a lot of skepticism has come from. That it's just this can't be true. I cannot not have known this, or they cannot. And I think that James Hansen, that was the first response as well, and my own response as well when I learned about his regulation like this. Can they just reduce sulfur emissions from one day to the next, from starting January 1st with 80%? Like, but then if you start to study the industry, if you start to study how desulfurization of oil works at these oil refineries, and how these markets work, and how this International Maritime Organization regulations work, and it's happening, and it happened, and it may be not as much here, or maybe a bit more there, or maybe there's some ships, some dark fleet from Russians still burning the dirty stuff, but overall, this has happened. And then what we said in 2021 and 2020 is like, okay, what will be an important indicator is how much sunlight will be reflected back to space, or how much that changes. And we didn't know what the real answer was, because, and there's a lot of modeling studies, but they're all over the place, so nobody knows, right? The uncertainties are just too large in a way. And I can talk for hours about why these uncertainties are so enormous. And a very important aspect, I think that maybe just show you this, I think that will help answer that question. So because this is Jin et al. Is this from the paper from Jin et al. And he is also co-author of Global Warming in the Pipeline. And we also included this graph in Global Warming in the Pipeline. And this shows total global sulfur emissions from natural sources and anthropogenic sources. And on the right, it shows how much of that, the percentage, what percent of that is from shipping. And then you see that over the North Atlantic and over the North Pacific and North Atlantic, a vast majority of the sulfur emissions, the sulfur load, is from shipping, or was from shipping.
Of course.
But there's quite a lot of uncertainty in the background load from algae. Because there's natural aerosols as well. There's natural sulfur emissions as well, especially from algae or from other ocean plants mainly, that also emit a lot of sulfur into the atmosphere, and that's very, very uncertain how much that is. That could be about the same amount as shipping, or it could be 5 times as much as shipping, or 4 times as much as shipping. And that really changes how much the impact of shipping emission changes are, because it changed the relative baseline where these emissions from shipping compete with, in a way, to cool the earth, in a way, right? So I think that's.
But the algae would be distributed across the globe in all the oceans, right? Whereas this impact is focused on the North Atlantic and North Pacific. In some sense, you might be able to estimate it.
And then the question is, okay, how much sulfur is where? Like, how much algae are where? And that depends on the nutrients, and how much nutrients are there in the ocean.
Temperatures and things like that.
And wow, how much whale poop is there to feed the algae, and so there's an enormous, and you can talk about aerosols from the Sahara, which during certain months, sunny months of the year, blow a lot of dust over the North Atlantic, and also cause fertilization of the ocean, which also produces algae. And so it's true. It's quite complex, and so it's very understandable that this has raised a lot of skepticism. Of course, some are skeptic and start studying it and try to prove us wrong, and we also try to prove, just trying to understand. So we're saying this is this much, but now that we are starting to estimate how much it is, others can have other estimates, of course, also based on the same data. And of course, there's always parties who are just saying, you're wrong, Like for me, for example, I'm a relative outsider, right? I'm a relative outsider. So what does this guy know? Right? Yeah, I at least I knew
Well, Jim
this was
Hansen's not a
happening, right?
relative outsider, and
Sorry?
he Jim Hansen's not a relative outsider,
No,
although
no.
I guess sometimes he's treated like that. But
Yeah,
he did say that I think it was Zeke Hausfather's estimate and your estimates were off by factor of 10. So he said we're going to find out soon who's right because when something's that big a difference, and then the data comes in, which is coming in like 2024. I mean, we're getting the data in. I also think that the chart you showed previous, not today, of warming by latitude and showing this essentially a new El Nino forming, a permanent El Nino in the North Pacific, North Atlantic region, which is just getting so hot
yeah,
that
yeah.
it seemed like I guess if you disagree with the hypothesis you're putting forward, you should have your own, right? You should have an alternative theory of why the North Atlantic and North Pacific is getting so warm relative to everywhere else. I haven't
Exactly.
heard any alternative
Yeah, so
theories.
I think the one of the alternatives is that it's cloud feedbacks.
Oh, right. I want to ask you about that. We're going to
Yeah,
have next week, we're having George Salutis on from NASA climate scientist who recently published a paper saying that warming is causing clouds in intertropical zone to narrow, which increases warming. In other words, warming is causing less clouds in key regions, which contributes to more warming. And some
yeah.
people are
What
getting
causes
that
the warming?
confused
Then the
with
question is
what.
what causes the warming, right? So
Well, no, I know. I think that's global warming. I mean, that's man-made warming, right?
yeah, yeah. So I think, but so George is a co-author of James Hansen.
Hmm.
He's co-author of the Global Warming in the Pipeline and co-author of
Hmm.
the study that will soon be published. And yeah, so I look forward to hearing him discuss it. And I think what's very important to note is that um, we our estimates, if you estimate that aerosols cause an increase in absorbed solar radiation, that doesn't mean that there's no role for uh, feedbacks.
Of course.
I don't say 2.3 watts per square meters of additional of this increase in absorbed solar radiation is completely due to aerosol reduction. It's due to less sea ice, less snow cover, less clouds, and less aerosols. And the cloud effect is quite uncertain. How much of that is from warming? Because if you have warming, the clouds evaporate or uh, they rise, and the low clouds reflect more sunlight and radiate more heat to space than higher clouds. So there's these different aspects of clouds also from warming, and that's very real.
Hmm.
We're not denying that happens. We're just saying we want to learn how much of it is relatively due to aerosols or due to clouds, and there will always be uncertainties. So how much of that is due to changes in wind patterns, and there will always be uncertainty. But what's very real is the increased rate of heat uptake, because that's what all the data sets show. So there's more
Hmm.
heat accumulating in the system, and that's causing faster feedbacks, and that's causing faster warming, surface air temperature increase, also more infrared radiates to space, Planck feedback. So all these things act together, and I think that I have another slide on that as well.
So this is really important. I mean, I think people are oversimplifying sometimes and saying, I don't know, Leon Simons and James Hansen said it's ships, and this guy over here is saying it's clouds, and who's right? That's not the question. Is that all of these things contribute, and as you're saying, the interesting question is not which one is it? It's how much of each one is it? Because all of these things, I guess the analogy would be you have a car and you haven't taken care of the brakes, and so the brakes are worn, and then you're driving on a wet road, so there's less friction there, and then you crash into a wall. Was it the brakes or was it the wet roads? Well, no, it was
or the
both,
speed, or the, yeah.
what speed and all these other things. So,
Indeed, and
uh,
that's very simple. You know, that's very simple. There's one car going straight, driving on one road with where the circumstances are very easy to understand, because you can look at the road, you can look at, okay, how much water is there, you can do some analyses, you can look at the tires, you can look at how much, how worn the tires were, how worn the brakes were, how fast the person was driving, what their attention were, whether they have been drinking. A lot of uncertainties, a lot of known unknowns, but you know, there's not a lot of uncertainties if you compare it to the global climate system and our
right.
impact on it, and all these different aspects interact. So I think many, like, I understand it for some journalists who's never written about climate, who just writes a headline and misunderstand it. But sometimes, you know, if I see new scientists say that there's record cooling of the north of the Atlantic, you know, that's quite disappointing sometimes. That some, like the more respectable news sources, but also often climate scientists who should know better, who are just yeah, I think in a way misinforming the public about crucial changes that are happening while we are here. And like, I'm not talking about Zeke, but just say, for example, to go back to your point on how much, what did we, what explanation is there for the warming? As I showed, not knowing how strong this El Nino was, but Zeke underestimated the warming by about 0.2 degrees Celsius.
That's a big amount
Going
when you're
back
talking
to
about
your
the global
question
temperature.
about this tenfold estimate of James Hansen of compared to what Zeke estimates, right? So Gavin Schmidt also underestimated. He said, I cannot explain 0.2 degrees Celsius of warming in 2023. Also, in a way, referencing Zeke. So, in a way, the one and the same source saying, we cannot explain what's happening here. But yeah, if you look at the data, if you look at where it's happening, if you not just look at global surface air temperature change, but if you look at the regional aspects, what let me go back to my slides. Then I don't think there's many other conclusions you can draw than that this does play a significant role, more than 0.5 or 0.1 degrees Celsius of temperature, global temperature increase, especially regionally, because that's, of course, the North Pacific Ocean. So these are the regions where we looked at in detail, right? And yeah, I wrote already, I gave a presentation about this in 2021, where we saw these two regions, North Atlantic and North Pacific, where the vast majority of the sulfur emissions, or the relative majority also of the sulfate aerosols, are contributed by ships. And if you look at the global, so this from the Copernicus, the CAMS estimates, where you see the global sulfur emissions, well, they were already decreasing from shipping, but then they nosedived in 2020, and then and also from this done the 20 to 60 degrees north, which is almost 50%. 50% almost of the total emissions are over this region, right? And it is not typically see a part of it can be explained by a variability of the Pacific Ocean, but now it's negative. It's the Pacific decadal oscillation is the most negative it has been in 150 years.
Wow.
So you would expect this black line, which is absorbed solar radiation, to decrease, but instead it has very rapidly increased. This is the four-year running average to decrease the variability. Otherwise, you just see a lot of lines going up and down. And it is red. In red is the outgoing long wave radiation, which increases with increasing temperatures. So as there's warming, there's more infrared radiation space. But the imbalance increased by 2.3 watts per square meter over 37 trillion square meters.
So, so let me ask you a question about all of this that I actually been meaning to ask you for a while. This is a step change. You know, you're going along here and boom, but then it continues on. It's not getting, well, emissions from ships are not going to keep getting lower. I mean, they might a little bit, but it's not
They
going to be
will.
like what we just saw. It's a step change. So when you talk about
Yeah, this is.
accelerated warming, you would expect a short-term acceleration, and then you would expect it to continue on the path it was before. But I believe that you and Jim Hansen and others, you're proposing that we're actually in a new regime of continued accelerated warming. But how can you
Well,
talk about that? The
that
step
depends
change
on.
versus continued
Yeah, so
accelerated warming.
I think this shows. Like, the paper is called "Warming in the Pipeline," right? And
Hmm.
this shows that there's still an increase in the imbalance or the increase in the net flux. So how much radiation goes out and how much is absorbed. This increased a lot,
Yeah.
and this hasn't decreased in the past 4 years. It has only increased further. So we shouldn't expect at least this region, as long as this either the for outgoing long wave radiation increases to be the same as this, or the absorbed solar radiation decreases
Hmm.
to be the same as this. And otherwise, there will be an increase, a continued increase in warming, because this is a regional.
Right, right. Because the warming is the difference between those two lines is what's causing the warming. And it used
Yeah,
to be
no,
relatively
but
small, and we're going up a
yeah,
little bit,
but
you
this is
know. Yeah.
just to clarify. So this is zero. Here they are the same. So this is the baseline. So this is
Wait,
the
where's
relative.
zero? Oh,
These are
there we go.
relative to zero here.
I
So
see.
that means that even there, right in 2024, there was a global energy imbalance of about half a watt.
Okay, okay.
So, but the increase regionally is 2.3 watts per square meter over
This is
the region.
relative to that 2004, basically.
Yeah,
Okay.
yeah, to 2000 to
Okay,
2004.
so then it wouldn't look as dramatic, but still there's an opening of the thing, so it is increased. There we go. That might be like a, well, it's not
Hmm?
better, but yeah, I understand. So now that it's a
Yeah, this is
step
just a different
change
region. This is the North Atlantic.
causing a more bigger energy imbalance, and it's the energy imbalance that
So
drives warming. So yeah.
so yeah, either we decrease greenhouse gas concentrations, or we
But,
increase aerosols, or yeah, we should be lucky with the feedbacks, right? That those are the different ways to answer your question.
mhm,
Either we have luck with the feedbacks,
which we're not going to.
yeah, and then if more of this is due to cloud feedbacks, I think that we have a bigger problem because we cannot really do anything about that. So from that perspective, I
Hmm.
would wish it's aerosols in a way, because then you
Why
could.
are you suggesting that we go back to dirty fuel for ships?
Yeah, that's what. So that I don't make policy recommendations, but that is something that if you would want to do this, if you would want to rapidly reduce warming of the North Atlantic or the North Pacific, or increase the AMOC, or stop rapid decrease from the AMOC, I could
Hmm.
cover that as well. Then that is one of the tools you could use. Because if you want to if you want to do it with salt particles, right, that you need to technology. But if you could, there is some studies saying, okay, if you do it, for example, further from the coast, where it doesn't have the
Health impacts.
environmental on land, on the environmental impacts on land, and the health impacts on land, if you do it further from the coast, then you might get the same or similar amount of cooling if you continue to emit sulfur particles over the deep ocean. You could have some cooling as well without the negative, or without most of the negative side effects. That's
Although
that is
once you
something
do
to.
that, now it's solar geoengineering because you did it on purpose. It wasn't solar geoengineering before because we weren't doing it for the purpose of cooling the Earth. But as soon as you add it back to cool the Earth, you're doing solar geoengineering. In which case, you might as well do it in the stratosphere, which has tremendous advantages much better for human health because you're using a fraction of the amount. And when it falls out
Yeah,
of this,
but that depends
listen,
a
by the
bit
way,
the way you
everyone
do
should
it.
listen to the program with David Keith on this. And he's going to be coming back, by the way, to talk about SRM more on climate chat. But he's mentioning that when you do stratospheric sulfur, two things happen. One is you need like 5% as much to do the same amount of cooling. And the second thing is it rains out as rain rather than air you're breathing. And so he has, and it's also distributed over the whole globe rather than concentrated where you emit it, like in China. So he estimates it's 1,000 times safer overall for human health than doing it in the troposphere, which is what the ships are doing and the coal
Yeah,
plants
but
are
then,
doing.
no, then also depends where you do it in the troposphere, of course. I think it.
Yeah, but ships are
If,
safer, probably. Yeah.
so
Okay.
if you start comparing different methodologies of sunlight reflection method, I think yeah, I think I could also make the case that if you do it on the right at the right location over the oceans, it's safer than if you do it in the stratosphere, right? If
Because it's
and I,
local. It's local.
yeah, it's
But
local,
local
but it's also
cooling has
it's
impacts
also exactly
everywhere.
where you want it to be, right? And it's exactly where it's local. It's very white clouds. You can have
Well, marine cloud brightening is another version of that too. Yeah, which is
yeah,
essentially what
it
you would
is
be
marine
doing.
cloud brightening. You know,
That is
it's
what it
actually
is. Yeah.
it is what it is. Yeah, you
Different
make
version
clouds over
than
the ocean
yeah.
brighter, which is marine cloud brightening. And some, yeah, of course, I'm not going to say that the all the ships are intentionally doing marine cloud brightening, but it's like
they they were knowingly doing it, right?
they will
It was for the purpose
yeah
of getting across the ocean, but we knew
yeah.
that the sulfur was cooling the earth.
I don't think we know a lot. That's the point. So, for
We don't know
example,
enough.
so on May 1st, 2025, there will be new regulation coming into effect over the to reduce sulfur emissions over the Mediterranean again with another 80%, where the maximum sulfur fuel content decreases from 1%, from 0.5% to 0.1%. That
By the way,
maybe
just to explain that though, does the Mediterranean currently have the 80% reduction, or
yes,
and so the Mediterranean is going from an 80% reduction to another
yes.
80% reduction?
And that might not sound like a lot if you compare it to the first 80%, but I think we discussed it before. The effects are not linear.
Right,
The
it's
effects are not
logarithmic, right?
linear.
Yeah.
If you spray paint a black car with white paint, even if there's a few microns of paint on it, it will be white. If
Right.
you add another centimeter of paint, that additional paint will do much less than the first
Yeah.
micrometers, right? And
Yeah.
it could be the same over the Mediterranean. I don't know. I have asked many people who should know about this, whether they know of any study on this,
Hmm.
and all of them were completely oblivious about the regulation, even like most
Okay, they
were.
didn't know that it's going to happen. Okay.
Yeah, like most were completely oblivious about IMO 2020 regulation of reducing the initial sulfur emissions over the ocean by 80%. Most are completely oblivious about what's happening over the Mediterranean on May 1st, 2025. And therefore, we don't have a lot of models, insights, preparations on what are the potential impacts of this regulation on the regional climate. And I think that I've used this word before. I think it's gross negligence. But yeah, I don't
Would you
know.
have a prediction though? I was going to ask you this. My question is like, first of all, this is like it's as if some climate lab somewhere said, "Hey, this is great. Let's do an experiment. Let's reduce sulfur even further in the Mediterranean so we get more data on aerosol impacts." Of course, they're not doing it
Yeah,
for
but
that reason.
even those who want to do those experiments are oblivious about this,
Well, they
right?
never would do that, right? It would be
No,
considered way
I
too
mean
dangerous to do,
those who
right?
would like to do marine cloud brightening experiments to build knowledge for the future when the climate is um, maybe warming at a rate we don't want, and or at we reach a certain temperature we don't want, and they when we or governments or certain stakeholders are even considering of doing intentional marine cloud brightening, those who are studying that or want to study that are oblivious about the regulation, which is the biggest pilot they could ever get, which you would never get approved if they want to do it in the real world, right? And I think that we should, or they should learn from this, and not just those studying sunlight reflection methods, but maybe even more, all the climate scientists who want to reduce the biggest uncertainty within climate science is what the impact of aerosols on clouds are. So we should really study this. And
do you have a prediction of what's going to happen though? Do you like?
I think it's the same on the IMO 2020.
I think there'll be a significant warming over the Mediterranean, which is really bad because it's already pretty bad in Greece and Italy. They're getting strong heat waves. Spain is getting very dry.
I've been on CNN Turkey to talk about this last year, and Turkey is also installing a lot of desulfurization system at the coal plants, and there is from all these different sources, those emissions are decreasing. And while almost no one, I've been at the regional water boards in the Netherlands where they are also you have these IPCC models, right? These CMAP6, and those are used to estimate global changes, and then and then, for example, the KNMI also uses these SSPs, these emission pathways, and to estimate what the regional impacts are. And then then there's other parties studying what does that mean for the Netherlands, for precipitation, for droughts, for how high our dikes need to be, for our drinking water, for all these things. So, but if the guys on the top, right, the IPCC models, CMAP6 models get it wrong, my water board doesn't build the right dikes. The Dutch water boards invest billions in building the wrong dikes for the wrong weather, not taking into account all these extreme rainfall, longer droughts, which will crack the dikes, changes in heat and in precipitation, so all these and yeah. So I think it's a global. All these different stakeholders, and I think that's why also where part of the denial comes from, because I also experienced that when talking to these representatives from the water boards, they say, yeah, we need to depend on the IPCC to get it right. Who else is there, right? If they get it wrong, and I'm sorry, but
that's true. That's true in general, right? We're relying. I mean, the phrase is "it's much worse than scientists thought" is a very standard phrase in the news, right? And that's because, well, I mean, Jim Hansen wrote about this, I think, in 2006, how science is set up to be conservative, not in the right way for climate change, but it's fine for black holes to take your time and figure it out, but by underestimating impacts, it's not working out too well for us, and that's continuing. By the way, I learned that I heard that Europe is doing the best job in terms of fighting climate and cleaning up air pollution and putting desulfurization on everything and getting rid of pollution sources and trying to go to renewables faster than everybody. And it's also the fastest warming continent. I understand. Like the land is warming faster than anywhere else. I think it totally ties into your work. I think it's
60,000 deaths in 2022, 50,000 heat deaths
from the big heat wave in France. Yeah.
In Greece, and so and this year again. I think those studying it. So it's not about me or Jim. It's this is the community studying this shows indeed that the data shows that there's an increased warming from the reduction in air pollution. And of course, that was hiding, we haven't mentioned that yet, but because it's a given, that was hiding the greenhouse gas warming, right? Because the greenhouse gases cause the warming. And the air pollution was hiding that warming. As long as we only reduce air pollution without reducing greenhouse gas concentrations, not even just emissions, but concentrate, there will be more, especially regional warming, because of those two effects. It's not just warming from reduction in air pollution. Right? In the scenario where the greenhouse gases would have been reduced back to the 1750 levels, there wouldn't be additional warming from reducing air pollution. So you have to take both of these into account. It's also, you could also say there is
the global warming, the pipeline paper, in essence, I think says warming from greenhouse gases is more than IPCC was assuming. Instead of like 3-ish, 4.8, which is a huge difference. Yet the cooling from aerosols is also more than the IPCC was assuming. So therefore, you measure the same net temperature, but one is based on this, and the other one is based on this, and
it's a different for net force, because the forcing, so the aerosols cause cooling, and the greenhouse gases cause warming. But if you have more greenhouse gas warming, you compensate it with more aerosol cooling. You end up with the same climate effects, but both the aerosols and the greenhouse gases have therefore, according to our research, a stronger climate impact.
Which is okay when they're canceling each other out, but as soon as you start cleaning them up, like they are for shipping, and how supposedly when we go to net zero, we're going to get rid of them. Oh, let me ask you that question then.
Can I first just...
go ahead.
Because I think this is one point, and this also answers part of your question on whether those who have been underestimating or have been skeptical about what we said, what we showed. Whether they will now start to be less skeptical. I think, in the end, you have to ask them. But so what this study shows is that this new study shows that the planetary albedo added 0.23 degrees Celsius or Kelvin, the same. 0.2. Of warming. So the decrease in the reflectivity of the planet caused 0.2 degrees Celsius of warming. And over the northern hemisphere mid-latitudes, that is about 1.12 in their estimate. And of course, then you can say, okay, maybe this region, maybe this. And I think much of this, if you look at the data, of course, we look mainly at the data here, sorry.
Right, that's a shipping
over
area.
this region, and there it's a bit of a cherry pick, but of course it's the cherry is where we know that most of this effect happens from shipping emission reduction. So, and it's still over 10% of the Earth's surface. Then you see that in this region where most of the shipping emissions happened, also including North America, where no ships are, of course, but just looking at this larger region, there's an increase in how much sunlight is absorbed on average over 4 years of over 4 watts per square meter relative to the first 4 years of the data set. And that, again, still 1.9 watts per square meter. So this is about a record, still at record high, the imbalance increase. And therefore, as long as this doesn't decrease, again, in this region, before I was just showing the Pacific, or this increases further, there will be much more regional warming in the pipeline.
Regional, I see that. Okay, and that. By the way, go back to the previous one.
Sorry,
the global picture, the previous picture. Also shows that it looks like the drop in Antarctic sea ice is having a big impact. There's a lot of black around right
This
above
Antarctic sea
Antarctica.
ice. Hmm?
No, the Antarctic, right above Antarctica. There's
This
a,
it's here, 0.02 Antarctic.
okay. But just in the picture itself, it looks like that's significant. What's happening in the Indian Ocean there? That looks like a big impact there,
Here.
but I don't know. Yeah. What's going on there? It looks like a big impact. I don't know.
Let's see if there's much sulfur emissions there. Yeah.
Where
But
are we?
we're back to sulfur emissions over the oceans,
Oh,
over
there we
India.
go. Oh, yeah, yeah. It is pretty big there. Yeah. Okay. All
Yeah, it's
right.
of course this eyeballing graphs is nice, but it's yeah, so but that's why you need to really studies to look at really specific regions, right?
Sure.
You and uh, and one of the regions is the North Atlantic.
Okay. By the way, we're going to move to questions in a moment. So if you're on YouTube, uh, and you want to ask a question, put something in the comments and preface it with question colon. And even if you put a previous question, please repost it so we don't have to look back in the comments. Same thing for Clubhouse and Zoom. And if you're on Zoom, we can also invite people up for questions. So, but we're going to start with Stacy. Stacy, if you're there and if you have a question and perhaps some question from the comments.
What was I still sharing my graphs or
Oh,
not?
yeah, you are still sharing. So turn that off so we can
Okay, so
see
you don't want to
everybody
see the
here.
Atlantic, you believe it.
Oh, I want to see all the data. Yeah, it doesn't look
Okay.
good. But this one, I think that was showing what I was talking about earlier, how aerosols played a role in the since the
I think
Industrial
the
Revolution.
one let me just cover this for few minutes. Sorry, Stacy. Hi.
Okay.
Um, just so I think this North Atlantic is quite important because that's where much of the skepticism came from of how much that this the increase in warming or the increase in temperatures over the North Atlantic, whether that was due to decrease in aerosols. And there was in over 1.5 years ago when there was quite a spike. But if you just look at the temperature normally of the sea surface temperatures of the North Atlantic, right? It hasn't come down. I excluded 2000 to 2023 to
Make it clear.
the
Yeah.
shifting baseline syndrome to address that. To see, it hasn't come down yet. So all these lines normally were just like touching down, but now it hasn't been down there. So it looks like we've reached a new baseline, and it could still increase further because there's this vast increase in the net flux. So much more energy being absorbed and going out. And also that also of course depends on how much heat comes from the south of the Atlantic through the AMOC. I think the AMOC is an important part there because the AMOC transports a lot of heat. That's about equal to that Jim told me that the AMOC is equal to a northern hemisphere incoming radiation of 4 watts for the entire northern hemisphere. That's 255 trillion square meters of the northern hemisphere times 4 watts. So that's how much heat is transported through the. I think I have
AMOC.
500 billion Hiroshima bombs per year. I think that was what I estimated.
By the way, we're having well, last week was it last week? No, 2 weeks ago. Gabriel Fontes, we talked about AMOC slowdown. We're going
Oh yeah, it was
We've
interesting.
covered it extensively for people interested in AMOC. Go check out past climate chat programs on AMOC. There's quite a few of them. And maybe have a drink first before you sit and watch them. So
Very good.
oh, speaking of, I guess my last question, I'll throw it in because you mentioned AMOC and you said that we could put sulfur in the ships and let's say just the central North Atlantic, let's say, to recool it. There was a paper recently that came out that said solar geoengineering with stratospheric injection would strengthen the AMOC. That's very
Yeah.
important because the first
I
research I
didn't
saw that,
include it here, but that aerosols over the northern hemisphere, that was because that was mainly aerosols, stratospheric aerosol injection over the northern hemisphere.
right.
So folks, and that would indeed strengthen or reduce weakening of the AMOC if you do solar radiation management or solar reflection methods over the northern hemisphere, especially the northern hemisphere's mid-latitudes, which is about the opposite of what we have been doing, reducing air pollution
We're
in
reducing
the
it. Yeah,
northern hemisphere
exactly.
mid-latitude.
Mm.
It is marine cloud brightening. This is exactly what you said, but then from marine cloud brightening, where you have if you do it over the mid latitudes, over the northern hemisphere mid latitude is focusing on the North Pacific. Maybe the North Atlantic will be even more affected. If you do it that would increase the AMOC or by about 0.1 or 0.2 watts per square. Sorry, petawatts. Sorry, petawatts. That's a petawatt is a joule per second with 15 zeros, I think, or was it 18? I don't.
It's
15,
a
15.
very, very big number. How about that? We can probably agree on that.
Yeah. And that's I think the AMOC by itself. Like I have it here. No, by itself has a strength of about before it started weakening of about 1 watt, 1 petawatt, 1 petawatt. So that's those
Hmm.
500 uh 500 I don't know 500 million per year. I have
I
it
think
on.
there's a data that shows that increasing reflectivity, however you do it, whether you do it with ships or with airplanes or what ocean water
Or air pollution. So
pulverization
this
or
was air
whatever.
pollution, right?
Yeah, yeah.
So
So
this was
however you do it, it's going to strengthen the AMOC. And as we get more and more scared about the AMOC, which we should be, I think this is going to change the discussion of SRM quite a bit. So,
yeah. So
okay.
historical aerosols from CMIC 6 strengthened the AMOC by about 3 on the peak, over 3 sverdrups, which is what is it, a million cubic meters per second.
Oh, I see. Oh, greenhouse gas is hurting, and then aerosols are helping. I see.
Yeah.
Natural is okay. Huh.
So there's
Okay.
acceleration of weakening of the Atlantic overturning circulation.
An
Yeah.
ozone. Okay. Cool.
So sorry, just showing the few Atlantic graphs. So these are going back 150 years, sorry, 150,000. So about the time when this guy in my neighborhood started looking at these drill cores from these wells to discover the amine, right? Since that period, about 2010, that warming over the North Atlantic, we experienced the same warming in the past 15 years. So
Hmm.
that's a tenfold rate of warming in a way, right? So of course, there's variability, but it's indeed was also aerosols and there's some data uncertainty here. But I think that's really important to take into account that 2024 was warmer than the extreme year of 2023. I think this is an interesting study of the Atlantic Ocean, the multi-decadal oscillation of the Atlantic by someone who was a bit skeptical about the sulfur emission reductions, shows that so-termed Atlantic multi-decadal oscillation is instead a manifestation of competing time-varying effects of anthropogenic greenhouse gases and sulfate aerosols. And I think that's really important to take into account because if you look at this AMO, the Atlantic multi-decadal oscillation data sets, those are really off the charts as well. I didn't include it yet here, but it's
When
it's
did
it's mainly a sea surface temperature, so it's similar to this, right? This graph, it's really off the charts.
when is that paper from? Is that a recent paper or is that older paper?
2021,
Okay, so a little while ago.
but yeah, I don't think they wrote about shipping emissions,
Hmm.
which is quite important if you look at the Atlantic Ocean, because that's where about 40% of sulfur emissions from shipping happens, and ships are
Hmm.
the only direct emissions of sulfur over the ocean, of course, from anthropogenic sources.
Okay.
Okay, so more there, but let's not
Well,
get it.
any near-term predictions for 2025, 2026? It's still gonna, I assume you're thinking we're still gonna be this point 0.2 jump at least above where we were. It's like a,
Yeah, so the question is always like, what will the natural variability do? But we know the solar cycle is now at its maximum.
right.
So and that will still have a lot of that might have more effect in 2025 than in the past 2 years.
Mm-hmm.
So I don't think we should from that natural variability. I don't think we can expect less warming. I think it's likely that we'll see more warming from there. Of course, then there's this the El Nino, the La Nina. We are now, if you look at this relative data set, I'm just scrolling back to show you it again. If you look at the relative data set, let me just put it up because it might help to understand this better. So this peak of this, let's focus on the orange line. So this peak of 1.5 that did contribute to the temperatures in 2023 and 2024, of course. So and now we are at a La Nina, and it will go down a bit further, I think. But I don't think we will have a La Nina as strong as the recent years, as in 2000 or 2001, 20 or 2022. Sorry, 2020 or 2021 and 2022. This was quite a strong La Nina. I don't think, and there's still a lot of heat in the system, and the Earth's energy imbalance, looking at the NASA data, is still positive, even with this increase in temperature and the increase in outgoing long-wave radiation. It's still net positive, so there's still that, which means more heat is accumulating still, even while the planet is so darn hot, right? So that looking at those effects, I don't think that 2025 will be cooler than 2023 was. I think it will be, or much cooler. And again, that depends on how negative this La Nina will be and some other variability. But if you look at the past months, where am I here? These were still 1.7, 1.6, 1.6, while we already are in La Nina territory or close to La Nina, depending on, right? So, and I think next month will also be about the same, about 1.6, 7, 8 maybe, because it could be higher than so. Yeah, I think this will still be a very, very warm year, and I think that might help also to reduce some of the skepticism, and maybe also help to start working on faster adaptation, faster mitigation, and possibly also studying at least methods of reducing the risk through other means. Whether you say sort of sunlight reflection methods or some say it's building ice. Yeah, I think that you can talk. You've had many conversations about that already, but yeah, I think we need to do a lot more.
Very good. Well, a very appropriate place to stop that part and move on to questions. So Stacy, take it away.
Oh my goodness. Thanks for being here, Leon. This is, I believe, one of our highest attended live that we've had, and questions out the wazoo. So I will leave my question in with some of these that I've organized. There were, I'll start with the ones that are, around the aerosols. And some of this you've gone over, but just a quick recap, I think would do it. Someone is asking if this has worked its way out of the system, or is this an ongoing effect, the reduction of aerosols?
Yeah, I think I did cover that quite broad, quite widely as well. But let me show this graph then, because it's yeah. No, let me just So this is better. I already showed the graphs where you see the increase in net flux, which means increase in energy in regional imbalance, let's say, which means that there's still a lot of warming in the pipeline as long as the increase in sunlight reflection, the decrease in albedo, which means how much sunlight is reflected, as long as the decrease in albedo is not reversed, we should expect that temperature will keep increasing faster, or as fast maybe as they have been the past years.
Because we don't have that cover anymore.
Yeah,
Correct?
we don't have that cover anymore, and we keep increasing greenhouse gas concentrations like there's no tomorrow, right? So that's always important to highlight a few times, that without those are the knobs we can turn, right? Increasing how much heat goes out or reducing how much heat comes in. And it's much easier to, I don't know what's easier. That's a value judgment, but
right.
So this increase in, like, I don't think 2024 will be as high as 2023 was. You see my graph here, but yeah, I think this takes quite some additional warming to compensate for this. Yes.
And so a lot of it is around the timing, how long these things take effect. Sorry, go ahead.
So if you look at many of them, if you look at climate model estimates, right? Because of course those are the tools at hand are often climate models where we can estimate how long it will take for forcing change. So if you increase greenhouse gas concentrations by an X amount, for example, I don't know, trillion tons of CO2, or how much warming does that cause, and when will this warming materialize over which period of time? And so we have that, of course, for greenhouse gases. It's also part of the global warming in the pipeline paper, where you can see it, that it's about I think 50% happens in the first decade, and then after that, gradually the rest will, in a sort of logarithmic way, less and less, more and more slowly materialize that warming. But for this, it's in a way, I think it's different. We cannot just take what we learned from a climate model looking at greenhouse gas forcing change and apply that to a forcing change over the oceans, or aerosol forcing change over the oceans, because the oceans are different. The oceans take longer to warm, and because it takes a lot of heat to warm the oceans, and so I think and then there's different feedbacks over land and over the oceans, because you have much more clouds covered over the ocean. So you have more cloud cover. I think there's also more cloud feedbacks over the oceans. So that will make it, and I think that's also why it will be interesting to hear what George has to say. It makes it very hard to estimate what causes what, right, and whether it's a forcing or a feedback, and how long it takes. But so I don't have a very satisfactory answer, I think. But what I do show with the data, which the plots I already showed here, is that there's still, I don't think, like, the red hasn't increased quite as much as the black has. Here it has increased a lot, but still it's not way up there yet. And of course, in a way, you can see that how much the Atlantic has warmed, but I think there's still, right, how many years does it take for the Atlantic to warm as much to compensate for this additional 1.4 watts? And does that cause more cloud feedbacks, which cause additional increase in absorbed solar radiation? So I think I think the answer is it's likely that it will take quite a while longer, and we will have to face this increase in reheating rate, especially over the northern hemisphere mid latitudes, for quite a bit longer as long as we don't change our ways in unimaginable fashion.
So, and we're in kind of a pickle because we, to revert, as you mentioned, and Dan commented, it's like, if we were to reverse the decision, people are saying, well, if this was a mistake, then just put it back, that would actually be solar geoengineering, which everybody gets very upset about, because then we would knowingly be doing this to modify the climate. And even if we did, how
I don't
long
see
would
it
it take
happening.
to take effect?
Yeah, so I think it will have it could have a very significant effect very soon. Depending on how you do it, where you do it, to what scale, right? But like, if we cannot even talk about what's happening now over the Mediterranean, if even the most climate scientists who study this, who studies intentionally causing cooling, if they are completely oblivious about what's happening over the Mediterranean, and like, how can we start talking about doing it intentionally? I don't know, but you could have some crazy people think, okay, even we don't know anything, we don't know a lot, but let's do it, right? That's possible, but yeah, it's a hypothetical question, and I don't know. Yeah, I would like to know. I think what we really need to do is study in great detail what's happening now over the oceans globally, and pay special attention to what will happen over the Mediterranean. It's not representative of the global oceans, but I think it's quite an important ocean, because it creates a lot of weather for regions which are quite dependent on agriculture or growing their olives and their wine and what do they eat in figs or what? Pineapple. I don't know what it like. All around the Mediterranean, there's a lot of food produced, and there's a lot of people living there. So I think we should pay quite a close attention to what's happening there as well, and we should learn from that to try and understand first what the aerosol forcing in general is, and how we can reduce uncertainties in climate models. And a second, maybe to also learn from what would happen if we would do it intentionally.
That
Okay.
leads into a question from someone you may know, Pritam from UVA Amsterdam, asking, what do you expect is in store for food production in India, Bangladesh, and Southeast Asia generally?
Yeah, I think what's the biggest uncertainty there, I think, and again, something I haven't seen any study on, is also about reducing sulfur emissions from the coal plants of India.
Oh.
So in these northern, there's this band, this food belt in North India, Pakistan, Bangladesh, Bhutan, where I think 2 billion people, 1 or 2 billion people live and grow their food, and which is highly dependent on the monsoon rainfall. And the monsoon rains shift when you decrease or increase air pollution. So if you increase air pollution, monsoon patterns tend to shift northward. If you do I say, yeah, no, it's southward.
So this is something we would have witnessed already, because air pollution would have increased, I guess, relatively recently in India, as industrialization took hold there, right?
Yeah, so it's a global effect, right? So it's global warming and the northern hemisphere warming and global aerosols and regional aerosols. All these play together in changing the regional climate as well. And yeah, for that, I think the question, I think, is should really be asked to those studying the regional climate of this region, right? They should study what and taking into account the real forcing changes, not just the IPCC SSP 8.5, 2 point, or whatever, but looking at what's happening in the real world. And that's very hard to know because, India, around the capital, around the cities with 10 million or more inhabitants, which they have, I think, quite a few of, but especially New Delhi, or above a million, sorry, it's at 10, above 1 million should install desulfurization systems at their coal-fired power plants by the end of December 2024. Well, some have already, but I think, and then now there was a study or an article. Yeah, we want to postpone it again for the third time, right? To implement this regulation because sulfur doesn't cause that much health effects. Incomplete combustion of agricultural waste and cooking is much worse. So let's focus on that. Yeah, maybe, but I think I don't think they didn't write anything about climate, but that's, I think, those questions like what do all these cooking fires, these billion cooking fires in this region, burning every day, making chapatis and rice, what impact does this have? What will they change to different fuels or not? It all matters. I think maybe Professor Ramanathan can answer that question in more detail.
The one thing that I'm interested in, someone asked about is anyone looking at the emissions and on rocket and satellite launches? What is that impact and how is that affecting?
Yeah, that's in the beginning of the year, I was at the European Space Agency to talk at a conference about this. In part about indeed what do the rockets burn, but what's quite interesting, there's very little data of what's in the stratosphere and above, because you have the troposphere and that's where our weather happens, but then about at 10 or 15 kilometers altitude, the stratosphere starts, the higher altitude, and we don't have many ways of acquiring data from this layer of the atmosphere. There's some military missions taking some samples, and then it's quite interesting. There was this, so you have all these aluminum particles, because much of these satellites are made consist from aluminum in the stratosphere. So because all these when these satellites burn up, when they are retired, they are put in the stratosphere or in the higher altitude to burn up and then fall apart, because otherwise you would have all this space junk and you cannot. Yeah, that's dangerous also for space travel and other satellites. So they put all these satellites, they just burn them up in the atmosphere, which is, of course, there's also meteorites doing the burning up in the
Quite
atmosphere. So those are other particles which they compete with. But then what was quite funny was that all these particles are coated with sulfur. And for 2 days we were talking about all these satellites burning up in the atmosphere. And then I gave my presentation and I said, like, yeah, maybe we've heard a lot about all these particles and all these aluminum particles coated with sulfur, but we haven't talked about where this sulfur comes from. And these are, of course, the volcanoes putting all this sulfur up there in a way naturally. Like million or sometimes 100,000 tons, sometimes 1 million tons of sulfur with large eruptions being added to the stratosphere and then raining out over the years. So yeah, there's all these different particles. Of course now there's not much satellites there yet, but now, or there weren't, but now there are plans to have, I think, 10,000 Starlink or 50,000 Starlink satellites, and then maybe a few hundred of European satellites, and the Chinese also want some satellites. So I think in the end it might add up. I think that's
Yeah, when I worked on satellites 40 something years ago, it was if there was a launch once, twice a month, that would have been maybe a lot. Now it's about once a day. And with the new Starship, it's both, which is totally reusable, so therefore very inexpensive to run, it could go up even more. Still, there's 100,000 airplane flights every day. So there are things that are
That
really
was
quite big.
that's my question. Yeah. So I was going to take it down a level from space into air travel because I mean,
100,000 flights a day.
Lord knows I just want trains, 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 trains. I think it's embarrassing what the US has done. And I wish we would follow a mode like France,
Or
banning
China.
all
China. Oh.
intercontinental flights. Or yeah, I mean the rail that's built
China
out,
built up its
it
thing much super fast,
staggering. Yeah.
like we did highways in the 1950s and 60s. But
And
anyway,
but we're on air travel, and I don't know how we're going to get off of that. But is there anything that, and again, no one, please don't mistake me. I want trains, I want planes to be only when absolutely necessary, if that. But that's unlikely to ever happen. Is there any way? I've heard about when planes are flown, how they are flown, in terms of their contrails, the suppressing them, or given the time of year and location, that they might be able to help in terms of cloud formation. Have you heard or anything about that in terms of how air travel could be policy driven so that it could be less of an impact, more of a benefit?
Yeah, it depends quite a lot on what time of the day these contrails are formed, and also the environmental circumstances where these particles are emitted. If you have more or less water vapor in the atmosphere, you have what temperature is there, and so you can see it. If you look at the sky, you see an airplane flying, and when you can see when it enters a layer of the atmosphere where there's more water vapor present, because then you start to see these contrails form, and vice versa. And so you can see that sometimes they last long, sometimes they last short, and then some have all these conspiracy theories about them. But there's yeah, what these clouds do is they reflect heat radiation back to Earth, and they reflect sunlight back to space. And the net effect is warming. The contrails, it's called contrails, not chemtrails. These contrails have a net warming effect, which is interestingly about similar to the global energy use of humanity, about 600 exajoule per year.
Okay.
So
Yeah,
two different things going on there, though. But
Yeah.
okay.
But there's no net benefit. There's no, or there's no. It's
No,
not
it causes warming.
It causes warming at the
right.
moment. So you could say, okay, you cannot fly at this altitude, or you cannot fly. And there's some studies doing it, or different fuels, but that's with all the planes falling out of the sky at the moment, I think that's that, and it shows that it's not easy. It's not easy to change anything related to airplanes. If you want to change the fuel of an airplane, yeah, that takes decades. I know someone who's working on jet fuel. No, that's it's quite a what do you call that? A very regulated market, of course, because there are a lot of lives at stake and a lot of market value at stake if you have planes falling out of the sky for whatever reasons, and
Well, I
especially
mean,
if it might be the fuel, or if it might be the changing.
Well, sustainable
We have,
aviation
yeah,
fuels, which is a
SAF.
big thing, but that
Yeah.
only changes the I'll say theoretical emissions because the CO2 comes from supposedly plant sources, biogenic
Right.
Yeah,
sources,
but you
not
don't you
fossil
don't you
sources.
don't change
It doesn't
much the
change. It doesn't
chemistry.
change at all the reflectivity of contrails or anything like that.
No,
It
and
doesn't.
you don't change you do not change the chemistry of the fuel much. I think
Yeah,
that's
it's essentially the identical fuel,
It's the
really.
equivalent of
Slightly
biodiesel.
cleaner, slightly cleaner.
Biodiesel for planes is my
Yeah, you can
understanding.
think of it like biodiesel
Yeah.
for planes. That's true.
And the all of the I took a tour of SFO, San Francisco's airport, and 90% of all SAF in the world is consumed by San Francisco. And they do it as a mix. And the presence of that SAF in the fuel that San Francisco uses amounts to, I think it's like 2% of all
Yeah.
their fuel. It's
Mhm.
like, it's so minuscule. And it's like, when you think about trying to do that on a global scale, it's like, I don't know how that's
Oh,
gonna
I'll make a
happen.
prediction, which I think many people will disagree with. I actually think that battery-powered airplanes are going to be a thing not too long from now because energy density of batteries is really phenomenal. I mean, not for your EV. I mean, it's getting better for your EV, but the things in the lab are above the densities you need to make airplanes possible with batteries. Right now, they think it's way too heavy to do it, and that's true today. But
But
10 years from
yeah,
now, these batteries specially for planes could be instead of what your car is 200 watt hours per kilogram or something like that, it will be 1,000 or 1,500, where the break points, I think, I understand, supposed to be 400 or 500. So anyway, that's a totally different subject. I want to kind of get
yeah,
back to
yeah.
I did
the
want to,
global temperature. Yeah, Eli.
yeah, a couple points back on space. I did look into that question a few months ago, and I agree with what Leon said. Like the like over condensed nutshell summary is that at present levels, it's probably not doing much, but if it scales up by a factor of 10 or 50, that's the range that's projected over some time horizon, it could start being significant. The one factor that Leon didn't mention that there isn't enough data on that I think is concerning is the black carbon soot that's produced by methalox. And I've seen estimates that can be as high as 5% on a mass basis. But again, the data is really thin, and it comes down to specific rocket motors.
So, any comments on that?
Yeah, I don't know how complete their combustion should be quite complete because I think they have oxygen tanks and yeah, but I'm not a rocket mechanic or.
So let's get back to the global temperatures. One of the questions, actually, a couple of questions, I guess, were on the same thing. Caitlin Witkowski of Bristol University is estimating the climate sensitivity, equilibrium climate sensitivity being 7.2 degrees C or K. In your global warming, the pipeline, you were estimating 4.8. The IPCC is using 3. Any comments on Caitlin's number and also any update? Is there any shift in the scientific consensus on what the ECS is?
What is consensus?
Right. That's true.
Is
Any
it someone
any more scientists
else?
coming on board? Well, actually, I think we're going to talk to George next week about this, but I think his paper is basically suggesting that the ECS is higher than 3. It's up in the
Yeah.
4s. Yeah.
I don't have a good slide here now for that, but
No, just what your thoughts
yeah.
are.
So indeed, I think the climate sensitivity, I think, is much higher than most think. Yeah, it's we've increased the greenhouse gas forcing to a level likely not seen in millions of years.
Mhm.
And there's a lot of uncertainty what happens to a system if you do that, right? If you let alone to a to a planet with a lot of life and a lot of people on it, and how they react to that, and yeah, so these aerosol forcings also change this. So if you would, because if you have a model, if you have a climate model which doesn't use aerosols or assumes something about aerosols, well, what happens in the real world is there's a lot of aerosols over the Northern Hemisphere or only a part of the Northern Hemisphere. That changes also the climate sensitivity. That also changes the pattern effect, it's called. So where does the heat go, and for example, if you have more heat in a certain region of the ocean where there normally are a lot of low-level cloud decks reflecting a lot of sunlight back to space, and where they normally would reflect 90% of the sunlight instead of the dark ocean below absorbing 90% of the sunlight. If much of the heat goes there, then that has a stronger effect than if the heat goes to the Sahara Desert, which is already 40 degrees and which radiates all this heat directly to space because there's no clouds and there's no water vapor. And then the effect is very different. And therefore, to me, I think that's an important part of the discussion. You know, personally, I think whether Earth climate sensitivity is 2 or 10 in a hypothetical model, I think for scientists, for scientific discussions, it can be interesting, but I think there's been way too much attention at the Earth climate sensitivity part of the global warming in a pipeline paper relative to all the other aspects, which I think are much more important. Regional warming, regional changes, the paleo climate aspect, you know, all these. I think that we don't live on the global average surface air temperature. That's not what determines our lives. It's the regional changes. It's the sea level. You know, if the AMOC shuts down, for example, I think I mentioned it before. If the AMOC shuts down, that could reduce global average temperatures. And then you say, okay, Earth climate sensitivity is not as high as Hansen et al. Thought, because global average temperatures are decreasing while the greenhouse gas concentration has doubled, right? But then we know that if the AMOC shuts down, the Earth climate sensitivity might be lower, but the effects on our lives in the Netherlands, but in every coastal city, low-lying islands, is much bigger if much of that heat, instead of going to the North Atlantic, stays in the South Atlantic and helps to melt the West Antarctic ice sheet, for example. So,
Sure.
yeah.
Okay. By the way, let me make just a quick break here and let everyone know that if you want to follow Leon's work more and support him, there's a link to his Patreon page in the description, the video description. Also, please follow and follow our channel and like this video so it gets spread to more people by the algorithms out there. And also, you can follow us on Twitter and Blue Sky, both Leon, myself, and Stacy, and others, to just keep track of the new programs. And as I mentioned, upcoming next week, we have George Salutis of NASA, who's working on how clouds are decreasing due to warming, and that's causing more warming. He's also a co-author with Jim Hansen on the upcoming paper, and we're going to have Jim on. The date hasn't been set yet to talk about that paper. So a lot of cool stuff happening on Climate Chat. So stay tuned and follow us. So let's invite Dr. Brian here for a question for Leon.
Sure thing. Greetings, Leon. Good to see you. Actually, I was
Can't hear you very well.
Yeah,
Hi,
you
Brian.
speak up a little bit, Brian.
Okay.
Yeah, good to see you, Leon. Stacey, I was responding to one of your earlier comments about why we're not seeing more effect of India burning more coal. And I would look to Leon and James Hansen's paper, where he talks about underestimating the greenhouse gas forcing and underestimating the aerosol forcing. And the result, and I'd love to get Leon's thought on this, is that because of the delayed and amplified feedbacks, and because we've underestimated greenhouse gases, the increase in sulfur in over India and surrounding longitudes has simply resulted in less of the warming we would have seen if we didn't have those aerosols. And so it's been masked to some extent by the increase in CO2. That's my theory about this, but I'd like to hear if Leon has any nuances on this.
Yeah, I think the question was also about the monsoon changes.
Yeah.
Yeah, and I think
that's a key part. I'm glad you mentioned that, Leon, because I'm actually working with Dr. Sumitra Das at the Healthy Climate Initiative, and he's going to be doing half a dozen local outreach across cities across India to discuss climate choices for municipalities and regions in India and in the Bay of Bengal and in the Arabian Sea. So it's very timely because next month he's doing this tour across South Asia to discuss these very climate choices. So it is coming to the global south, as I believe, Dan, one of your previous guests in the past weeks, from a professor from the UK, asked for us to take the conversation to the global south.
Kevin Anderson.
Yeah. So
Kevin Anderson.
I was in India in 2007. I was 19 years old. I was traveling through India by myself, and I visited people there, and they invited me to their houses, and they cooked with the biomass fires, and I saw people cooking using plastic to cook their food, and that's also why when I started getting more in, that's why one of the reasons why I started studying tropical forestry, and why I focused on reducing biomass cooking and finding solutions for that through my social enterprise. And one thing I came across, and also in Nepal, was that these monsoon rains, they just, especially with deforestation, but also with changes in rainfall intensity already at that time, was that whole villages, and you see it now as well, often in the news, and of course it has happened before, even before we started changing the climate as much as we have. The whole village and whole towns are washed away by these enormous mudslides or these flash flood rains, and farmers growing rice and they are very adaptable. They live in the climate. They know the climate. They know that it can be very variable. They know it can rain, like rain that would completely destroy the whole towns in Europe. They're just happy that they have some rain for their rice paddies, right? So you really have to look at the country and the regional context, and so they are adaptable, and they change it. They can change also with the changes of the monsoon systems.
That's a great point, Leon. Yeah, along those lines, Dr. Das brought to my attention the failure of the monsoon in June and July of 2023. And or maybe it was 2022. And what was notable is that failure occurs in June and July when you have the greatest insolation in Bay of Bengal, for example, and it results in absolutely scorching temperatures and high relative humidity, resulting in a humidity, basically a wet bulb temperature approaching or exceeding 30 degrees Celsius. And it wasn't until mid-August that the monsoonal clouds finally came. So the failure of these monsoonal clouds have profound life-threatening consequences in the global south, like in these lower latitude regions. So I think the monsoon is the future stuff. Yeah. Thank you.
Yeah, and I think that's why this termination shock of India. India, like what happens to these rain bands, right? That's the point. Indeed, greenhouse gas increase. There's warming. There's more warmth coming from the south to the north, and bringing more rain, but also. And then these aerosols over Europe change, and then over America, and then over China, and then so it's very uncertain. Then again, there's very little research on that. I remember there was one study was showing during COVID, there was a decrease in activity with decrease in traffic and in industry. And there was a brightening over much of northern India of 16 watts per square meter on average for day and night. That's enormous. And of course, that if that's what will be permanent, and that's on the surface, if that will be permanent, that could have very, very significant climate and weather effects and monsoon effects for India. And again, we need the people who know the local climate, the local weather, the local meteorologists, local climatologists, to really take that seriously and to start looking into that and to prepare for that. Because even if they keep postponing their coal-fired power plant desulfurization, I think eventually it will happen when and they will need to do it, and they are doing it, but not as fast as they had planned for various reasons. But in the end, people don't want to keep cooking on biomass. They don't want to breathe this toxic air. They don't want to their statues of their gods being dissolved by sulfur acid rain, right? So in the end, they will also, like we have in Europe and in much of the rest of the world, introduce and enforce clean air regulations.
That's a great point, Leon. I think on those lines, there's a key thing there, and that is your excellent phrase of aerosol termination shock is something we need to bring to the fore. But then secondly, we should look at benign aerosols like sea spray and the role they can play, and actually, regenerating the brightness through benign aerosols like sea spray that could actually help to provide benign interventions. So love to explore that further.
Yeah, one of the questions in the chat was, are there other ways to cool the Earth besides sulfur emissions? And the answer is, yeah, there's lots of different ways. And that's one: marine cloud brightening, space-based reflectors, mirrors on the ground, micro bubbles in the ocean, which are kind of related to the sea spray. So there's lots of different things out there to be explored. And we talk about it. We've talked about it here on Climate Chat, a lot of programs on sunlight reflection methods. Leon, I want to thank you for enlightening us today and informing us. There's more questions, but we've been going on for over 2 hours. So I want to just thank you again for being a guest here. And there are links to some of our programs with Leon, previous programs with Leon in the show description as well. So check that out, and check out all our programs. There's a link at the very bottom to just sort of the whole set of Climate Chat programs. You're going to find that on AMOC, on solar radiation management, on accelerated warming, with all the top climate scientists in the world, and authors and advocates and all kinds of folks. And we have a great set of programs coming up, as I mentioned earlier. So everyone, thank you. Leon, thank you so much for spending the time with us. Again, you can follow Leon on his Patreon, and you follow him on X and Blue Sky, and keep up to date. He's always posting interesting graphs that kind of like shake you up a bit when you see them. But that's the world we're living in. So we're not really doing enough yet, but understanding it is a step forward. So, and Leon and Jim Hansen and others are helping us do that. So I want to thank you for all the work you're doing. And everyone, thank you for joining us here today. Leon, any final words?
Yeah, I just want to wish you all a happy new year already. And I think, what I had my New Year resolutions, maybe.
You want to share them?
Yeah, I shared them already online. I think I want to reduce my my personal energy content. So reduce some body mass.
Ah,
It's,
okay.
I calculated it's about 74,000 megajoules of energy I can lose. It's you know, I look at everything through energy from an energy perspective, and also your body also has an energy balance, which can as much what you put in and you burn about 100 watts per second. Well, 100 watts is 100 joules per second, so you can calculate that, and it's it's everything in a way like the global. Whether you talk about the global energy system or your body or your car or your house, those energy goes in and it goes out. And
Go here.
what I also
Ride a
ride a
bike.
bike.
That's
Ride a
one way.
bike. I mean, you're in the home of that, so
That's right. In other words.
no better way.
We're covered with riding a bike. We do that. And what I think, and you mentioned that to me as well, Dan. I think I appreciate that feedback. That I can be more open or less I don't know how to phrase it, but to climate deniers and to deniers about the rate of warming. I think I'm learning. I have learned that it's you know it's logical that people are in denial about the state of the world, because it's very hard to grasp and or to accept as well. And I think that's
Denial is
important.
actually increasing, which is kind of weird in a world that it's
No, I think
becoming so obvious that it's real. We're experiencing it directly.
I lost a lot of people close to me over the recent years, and I think many people I know have started to believe in God and in some supernatural, and to in a way to deny to the thought first were true or not, right? So, and I think it makes total sense that denial increases with the increase in harm from rapidly changing climate change, and also from people, like if you build a career around Earth climate sensitivity of 3 and it turns out it's 5, you don't want to be wrong, right? And because you also very much because you know what it means for your children and grandchildren.
Absolutely.
If it's 5 instead of 3 or even higher.
3 is bad enough.
Yeah, it's bad enough. Yeah. So indeed,
it reminds me of in the chat, they prescribed a song for us, Neil Young's "Helpless," which
Helplessly hoping.
As soon as I saw it, it's been running through my head, because that's the way it feels.
Well, again, we're focused on understanding what's really happening. It's not a lot of that's happening out in the world or in the regular media. And then we also talk about solutions. There are solutions, but we have to actually decide. I think, as Kevin Anderson put it, we're choosing to fail. And someday we might choose to succeed. I don't know. But once we do, I think there's a lot we can do. But for now, we're just going to sort of watch it unfold. And Leon's helping us understand what's happening. And I really appreciate that. So thank you so much.
Yeah,
Happy
so
New Year to everyone.
My third and last resolution is indeed work on solutions.
There we go. Okay.
Yeah.
And my New Year's resolution is to bring some more really good people to talk about climate on Climate Chat. And we're going to start off the year with a lot of exciting things. Thanks to everyone. I hope you do have a good New Year. And thanks for coming. And we'll see you next time. Thanks.